Suppose P is an odd prime. If x squared is congruent to A mod P has a solution, then we say that A is a quadratic residue of P. Moreover, there will be exactly two solutions to this congruence. So there must be exactly k quadratic residues and k non-residues. So given some odd prime P and some value A, how can we decide if A is a quadratic residue of P? While we could solve the congruence x squared congruent to A mod P, there doesn't seem to be an easy way to solve it. So let's consider a different approach. If P is not prime, then the greatest common divisor of A and P is 1 for any value of A, so the Euler-Fermat theorem applies. And if P is prime, phi of P is P minus 1, and so we know that A to power P minus 1 is congruent to 1 mod P. But if P is an odd prime, then P minus 1 is an even number. And so A to power P minus 1 is really A to some power squared. And let's sweep this expression A to K under the rug and call it Y. And so that gives us the quadratic congruence Y squared congruent to 1 mod P. And since P is prime, Lagrange's theorem tells us this has exactly two solutions, which are going to be Y equals plus or minus 1. Consequently, A to power K has to be 1 or negative 1. Now suppose A to power K is negative 1. Let's go back to x squared congruent to A. If we raise both sides to the P minus 1 halves power, we get, and so that gives us x to power P minus 1, but A to power P minus 1 halves is negative 1, and this is never true for any value of x. Consequently, if P is an odd prime, if A to power K is congruent to negative 1 mod P, then A is a quadratic non-residue of P. Don't even bother trying to solve this congruence because it has no solution. Now remember, consider the contrapositive. Suppose P is an odd prime. If A is a quadratic residue of P, then A to power K has to be something other than negative 1, and the only thing it can be is 1. So A to power K is congruent to 1 mod P. Now, that won't tell us if something is a quadratic residue, because here we're starting with the fact that it's a quadratic residue. So, what if A to power K is congruent to 1 mod P? By a similar argument, we obtain x to power P minus 1 must be congruent to 1 mod P, which is true for all x, but that doesn't mean any of them solves x squared congruent to A. Remember, when we raise both sides of an equation to a power, we might get extraneous solutions. So an equation like this, squaring both sides, but the solution that we get is not a solution. So let's try a different approach. Suppose A turns out to be a non-residue. Could A to power K be congruent to 1 mod P? Since P is a prime number, Wilson's theorem applies. So remember, Wilson's theorem told us that P minus 1 factorial has to be congruent to negative 1 mod P if and only if P is prime. And this was an absolutely terrible way to decide if a number was prime, but it does have other uses. So again, we'll assume that P is an odd prime. So our factorial will look like, now since P is prime, for any R, there's a unique S where RS is congruent to A mod P. Moreover, if R prime isn't congruent to R, then that other S prime is not congruent to S. Moreover, since A is assumed to be a non-residue, any factorization RS congruent to A must have R distinct from S. So these two k factors can be broken into k pairs, each of which multiply to A mod P. So we can form k pairs that multiply to a. And so that gives us a to the power k congruent to negative 1. So if k is a non-residue, a to the power k must be negative 1. And in fact, we can put these two results together and to say that if p is not prime, a is a non-residue mod p if and only if a to the power k is congruent to negative 1 mod p. And now, when we consider the contrapositive, we find that if p is not prime, a to the k is congruent to 1 if and only if a is a residue mod p. So we might try to find the quadratic residues of 17. Since 17 is 2 times 8 plus 1, we can evaluate a to the 8th for a equals 1, 2, 3, and so on. And this actually isn't much more efficient than simply evaluating x squared for x equal to 1, 2, 3, and so on. Or is it? Well, it isn't. So as far as deciding which numbers are quadratic residues, this doesn't really help us. On the other hand, if we want to decide whether a specific number is a quadratic residue, our theorem does help us. So for example, we might try to decide if 50 is a quadratic residue of 97. Since 97 is 2 times 48 plus 1, we can find 50 to the power 48 mod 97. Now, ordinarily, we'd find 50 to the 48 mod 97 using the fast powering algorithm. But let's consider a variation. Instead of finding successive squares and multiplying them together, let's find 50 to the 48th as the successive squares of something. What do we mean by this? Well, 50 to the 48th is 50 to the 24th squared. But 50 to the 24th is 50 to the 12th squared. 50 to the 12th is 50 to the 6th squared, and 50 to the 6th is 50 to the 3rd squared. And that means we want to start with 50 to the 3rd, square, 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 and square. Now, what happens if we do that? Well, 50 to the 3rd is 64, to the 6th, 22, 96, and 50 to the 24th is 1, and we don't need to square this any further because we're just going to get 1s thereafter. In fact, we might note that 96 is congruent to negative 1 mod 97. So when we found 50 to the 12th was congruent to 96, well, that's really congruent to negative 1. So when we square it, we're going to get 1. And what this means is we can stop if we get a power congruent to negative 1. But again, since 50 to the 48th is congruent to 1 mod 97, that tells us that 50 is a quadratic residue of 97.